Hello, everyone. Thank you for watching this presentation as part of eCAADe 2020 online conference. My name is Amir Hossein Rezai Charati. With my colleague and Professor Dr. Mohammad Javad Mahtabi-Nejad, I'm happy to present our article named SoRo Responsive Wall, Robotics for Human-Oriented Architecture. This research is done at High Performance Architecture Lab at TMU in Tehran. Let me start with giving a background of the core idea and purpose of this research. Looking back to the projects and studies done from the beginning of cybernetics emergence till now, we have noticed that most of the interactive and responsive solutions in architecture are related to maximizing human physical comfort and minimizing environmental impacts. Humans' mental comfort and satisfaction is lost in the technological innovations. So, we suggest a responsive structure to be used in public spaces for exhibition spaces as a shelter that integrates both physical and mental aspects of architecture. Regarding the methodology we've used to conduct this research, first of all, as I said, we had this main purpose and concept in mind, and then we studied the possible technologies that helped us to realize our concept. Between rigid and soft mechanisms, soft met our criteria. Then, for having a deeper understanding of soft robotics, we analyzed various case studies regarding their methods and materials. And after that, we went through design process and created three prototypes to find out the best solutions. And finally, we built a model in 1 to 15 scale to test our design ideas. Let's move on to the design concept. Our main concept in this project is to create a satisfying and comfortable place in urban spaces for people to feel protected and beloved. To do so, we want our structure to interact with people by its shape, material, and movement, as well as responding and adapting to environmental factors such as weather conditions and so on. In further slides, I am going to elaborate how we try to reach these purposes. First, I'd like to give a brief background on soft and rigid robotics. Well, this is a categorization based on their components material. As you can see in the picture, soft mechanisms are mostly consisted of soft materials like elastomers, silicons, etc. And on the opposite, rigid robotics contains solid parts like gears, cylinders, and so on, as you can see this KUKA robot in this picture. So the material gives each of the mechanisms different specifications. Hard robots can be used where power, precision, and speed are priority, and soft robots can be employed where flexibility, safety, and simplicity are important. So after studying the precedents of this topic in recent years and categorizing them by their application, we found out that there are two main approaches regarding building methods. As you can see on this slide, first one is the actuator itself shapes the body structure and creates the architecture, and the second one is the actuator are used to move or rotate another structure. Taking the first method in our mind, here this idea came up to our mind that what if the whole structure itself is soft and flexible? Most of recent projects also is important to say that they use silicon elastomers for their body, and they use their prototypes with silicon elastomers. But the scalability of the prototypes is a challenge because the silicon material is expensive, and molding and casting silicon in large scale is not feasible. So we took a step back and analyze the soft robotic actuator mechanisms and try to translate it to feasible, inexpensive, and scalable method for building structures. As you can see on the diagram, these actuators are consisted of inner air channels and a strain limit layer on one side. When the air channels are filled with fluid, like water or air, it starts expansion. And because the silicon flexibility, it can expand on one side, but not on the other side. So this actuator, this will cause this actuator to bend. To translate this mechanism into feasible one, we have proposed stretch fabrics for the body of this structure. It is where people start to feel this architecture, and so it has to be soft and flexible, and like it has to feel friendly and comfortable. And then we use airproof nylon or elastic balloons to provide the tension force for bending each column. And finally, any bendable and not extendable material can be sewed on one side of the stretch fabric, which in our model we have used plexiglass for this. And here in this diagram, you can have a better understanding of how the structure works. The structure measures environmental factors such as human presence, weather conditions by IR sensors, temperature sensors, and photocells to adapt itself and create a better space for users. So to conclude, we can state that this proposed structures is low cost, relatively durable, and can be easily prefabricated and deployed in every environment with various organizations. It is very light and also malleable, and it can be easily contracted and removed to other sites. And as my last words, we believe that with recent advances in soft robotics this year, interdisciplinary studies in this topic can open up a new line of opportunity for our future architecture. And that brings us to the end. I'd like to thank you for your time and attention, and many thanks to eCAADe team for making this year's online conference happen. Thank you.